Welcome to lecture 6. Today we formalize the mathematics behind absorption. Last time we discussed the physical process. Now we convert physics into quantitative measurements. The governing equation of analytical spectroscopy is the Beer-Lambert's law, often simply called Beer's law. This equation forms the backbone of spectrophotometry and analytical chemistry. Historically, this law combines the work of two scientists, August Beer, who established the dependence on concentration, and Johann Heinrich Lambert, who established the dependence on path length. The law states the absorption of light is directly proportional to the concentration of the absorber and the path length through which light travels. Let us examine the equation carefully. A equals epsilon times C times L. Mathematically, absorbance equals log to the base 10 of I0 divided by I. Let us define each term, that is, A is absorbance. Absorbance is a logarithmic ratio. It is a unitless quantity. Epsilon, the molar absorptivity. Its units are liters per mole per centimeter. Physically, epsilon represents the intrinsic probability that a molecule will capture a photon at a specific wavelength. The variable C is the concentration in moles per liter and L is the path length. In most laboratory cases, this is fixed at 1 centimeter because of standard cuvette sizes. We also define transmittance denoted by capital T, where T equals L divided by L0, I divided by I0, that is transmitted intensity over incident intensity. Therefore, absorbance is the negative base to the 10 of logarithm of transmittance. This is logarithmic scaling is what makes the relationship linear with concentration. Now, let us examine the limits of this law. Although the mathematics is elegant, Beer's law is not universal. It operates under strict assumptions. When these are violated, deviations occur. First assumption is monochromatic light. The incident beam must contain a single wavelength. If multiple wavelengths pass through, each may have different epsilon value, the linear relationship collapses. The second assumption is dilute solutions. The molecules must not interact with each other at high concentrations. Electrostatic interactions alter electron distributions. This changes the absorption cross section. And the third assumption is no scattering or fluorescence. The sample must not scatter light away from the detector. It must not re-emit absorbed energy as a fluorescence. Either effect confuses the detector and distorts absorbance readings. Fourth assumption is uniform path length. The medium must be homogeneous. The beam must travel through a consistent thickness without distortion. When deviation occur, they usually fall into three categories. First is chemical deviations. These occur when absorber reacts, associates, dissociates, or changes due to pH or temperature. Second, due to instrumental deviations, examples including stray light, imperfect monochromators, detector nonlinearity. Third is due to high concentration deviations. At sufficiently high concentration, molecules are so close together that their charge distributions interact. This alters their intrinsic absorptivity. Always remember, Beer's law works beautifully but not only within its limits. Let us now apply this mathematically. Let us consider a practical example. You are working with a dye solution from literature. You find that the molar absorptivity at 450 nanometers is 1.2 times to the power 4 liters per mole per centimeter. You place the sample in a standard 1 centimeter cuvette. The spectrometer reports the absorbance of 0.6. We need to find the concentration. We rearrange the equation C equals A divided by epsilon times I. Substitute the values. 0.6 divided by 1.2 times 10 to the power 4 times 1. Performing this calculation, 0.6 divided by 12,000 gives 5 times 10 to the power minus 5. Therefore, the concentration is 5 times 10 to the minus 5 moles per liter. This simple algebra is the backbone of quantitative spectroscopy. But remember the caveats. If the absorbance were measured at high concentration, say 0.5 molar, we would immediately question whether deviations were influencing the result. Always check the validity range before trusting the number. In the next lecture, we will begin exploring instrument design and calibration methods that ensure accurate measurements. Thank you.